Okay. Today's class is dynamics. It's called TAM 2030. Next year, I think it's going to be called MAE 2030 because the Department of Theoretical and Applied Mechanics was swallowed by the Department of Mechanical and Aerospace Engineering. It's dynamics. We have prerequisite of statics, TAM 2020, or Engineering 2020, which will be MAE 2020. I am your teacher. I've taught this class lots of times before. I believe all the information you want to know about the course is on the website. If it's not on the website, I probably don't know it, but I'll take questions about the course next lecture. If you want to find the website, I think there's a link to it in Blackboard, and if not, if you Google my last name, it will take you quickly to this course. My plan today is to give you an introduction to the subject, which is mechanics and dynamics and something about the skills, and then get right into the subject. Just some logistical things. We're going to use iClickers in this class. I'll ask questions now and then, so you should have them out and ready. The book is available at Crafty's. You walk into Collegetown, turn left at Dryden Avenue at the traffic light. It's on your right. It costs $60. If you feel like you need a review of statics, you can buy this book too there for $48. And the more you buy, the more nothing I get. So it's profit-free for me. Unfortunately, the book did not quite fit in the binding. Make sure that when you get the dynamics book, you also get the supplement, which is various tables and answers to homework problems and things like that. Comes free. It's a free extra. Any quick questions about basic logistics in the course? Like, for example, do labs start this week? The answer is no. Right. In fact, does this course have labs? The answer is, let's try it again. The time is scheduled, but they're not labs. They're going to be problem-solving sessions. It's a new experiment this semester. Okay, what is mechanics about? I like to think of it as a subject that has three basic pillars. And I'm going to make a table associated with these three pillars. And the table is going to have 3 rows and 3 columns. So they're the basic 3 pillars of mechanics. And in some sense, you can think of all mechanics theory and all homework problems, and this includes statics problems as well as dynamics problems, as divided into these 3 pillars. So the first one is what you would call material properties. Sometimes people call these constitutive laws. Sometimes people call those constitutive laws, as in it's what things are constituted of, what they are made of. And sometimes more informally, people call these force laws. So these are 3 different ways of saying the same thing. What are examples of this is things like you say the thing is a spring, and you might describe it with a spring constant K, or you might say it's a dash pot, and you describe it with a constant C, or you might say it's rigid, in which case you don't have any constants to describe it. It's a limit of infinite stiffness or of infinite damping. Or you might say that there's gravity. And if you're talking about gravity, you might be talking about near-Earth gravity or inverse square gravity. You might be talking about a drag law. I'll just call it C2 for some drag law, and so on. These are material properties. It's what lets you know the difference between, for example, a piece of steel and a piece of chewing gum. They both obey the laws of mechanics, but they have different material properties. The second material law is about geometry. Not the second material law. The second pillar is about geometry. Sometimes people include time in this. And another key word that goes with is kinematics. And it's about geometry in motion, or just geometry. What are the key ideas here are things like strain, or velocity, or acceleration. or angular velocity. Angular acceleration. There's probably more things like that. So I put a etc. here. And the third basic ingredient of mechanics is what we call the laws of mechanics. And there's a fancy word people use for this, which is kinetics, which is really confusing because it sounds just like kinematics, but the difference is kinematics doesn't have MA in it. Kinematics is about geometry, yet the word does have MA in it. So it's confused. It's just a backwards of a what's it called, mnemonic device. You say, oh, you add MA to kinetics to get kinematics. No, it's backwards of that. Kinematics has no mass times acceleration. Okay, what are the key ideas here? Are momentum, kinetic energy, and then one that we're going to use a lot later in the semester in ways that are maybe not quite familiar to you from your physics class is angular momentum. Okay, so this is the vocabulary, say, associated with these three branches. Then there's some equations associated with each of these. And basically, when you do a mechanics problem, a statics problem, a dynamics problem, a strength of materials problem, you mix and match these equations to do what you want. So what are the basic equations? They're equations like the tension in the spring is equal to K times the change in length of the spring, which people in physics class write F equals Kx, but that's a little bit ambiguous. Or you have the tension is equal to CL dot. Or you have that the force is equal to mg. Or you have that the second bucket, second sponge, just in case. Okay. That the force is equal to minus capital G over r squared. Or you have that the force is equal to c times the velocity squared if you have some kind of drag law. So there's example equations. How about for strain and geometry and so on? In TAM 2020, Engineering 2020, you had that strain was change in length divided by length. You also have equations like velocity is equal to x dot, or the velocity vector is equal to the position vector dot. Or we have that the acceleration is equal to the velocity dot. Or you have, in the right context, that the velocity is the angular velocity across the radius. And equations like this are kinematics equations. And then here we have the laws of mechanics. And there are mainly two that we're going to work with, but we can add a third. One is that the sum of forces on a system is equal to the total mass of the system times the acceleration of the center of mass. And the other is that the sum of moments on a system relative to any point C is equal to the rate of change of angular momentum with respect to point C. And then we also have that the rate of change of kinetic energy of the system is equal to the net power acting on the system. Usually people think of these two equations as the essence of what this course is about, the dynamics course, but we have to use all of them. Now that's what mechanics is about. Let me just see if I can take any questions on this. Next I'm going to tell you what dynamics is about more specifically. Any questions on what's on the blackboard or the basic logistics things? Okay, all those who vote A, please vote A. Just take out your, let me just see how many. All those in favor of B should vote for B, and all of those in favor of C, D, or E should vote your conscience. 88, 94, pretty good. Okay, let's just do some quick polls here. E, if you took statics in the fall. Anything else if you did not? How about B if you took it any other time? A, B, or C if you never took it? E if you took statics in the fall. E if you took it another, D if you took it another time. A, B, or C if you never took it. Okay, most of you took it in the fall. Okay, now another poll. A if you really like statics, and E if you really hated statics, and anything in between for, you know, C if it was kind of all right. That's pretty good if you're going to be a mechanical engineer. Now, you people should come talk to me. I'll give you a pep talk. Okay, statics versus dynamics. First thing, which is maybe depressing when you start a course like this, is the following thing, which I'll write in parentheses here. Now, the other professors get mad at me when I write this, but they have not been through the experience that I've been through, which is that when I started to write this textbook, we decided we would put lots of industrial examples in the book, and I talked to lots of people at lots of companies, and it turns out that almost nobody anywhere uses the stuff I'm teaching you in this class. Whereas, if we take statics and strength of materials, every engineer, mechanical engineer, uses this stuff all of the time. So if you've mastered the material from your last semester, you are ready to be an engineer. You can do useful calculations. The stuff this semester is interesting. I love it. I love this course. I love the material. It's conceptually mind-building. It's useful to you because if you get very good at this, it will build your skills over here, which is actually useful. It's conceptually useful in that it's a general case and this is a special case, but when it comes to actually taking the equations and skills that we're going to learn in this class, very few engineers do that in practice. They either do much simpler things or much harder things. Whereas the statics, the actual material you learn, bending moment is MC over I and stuff like that, all kinds of engineers use that all the time. Okay, so that's the first distinction. But what's the main distinction is the following, is that we have our main equations, which I call linear momentum balance and angular momentum balance. And those are horrible names for these equations, but this one says that the sum of forces, that is the sum of the external forces on a system, is equal to something. And in dynamics, we say it's equal to the total mass of the system times the acceleration of the center of mass. And in statics, we say it's equal to 0. So that's the big difference. Now, which is the right equation? This is the right equation. What do I mean by right? Is that this is much more accurate. This is just an approximation. Everything's accelerating. Now, of course, this is an approximation too, because of general relativity and special relativity and stuff like that. But this one will be accurate, you know, to 1 part in 10 to the 9th or so, whereas this one might be, you know, if you're going to look at the forces on me standing here, you might make an error of 1% or so if you use statics to figure out the force on my feet instead of dynamics, because I'm moving around a little bit. Why is this thing called linear momentum balance when there's no linear momentum anywhere in the equation? Is because this term here is the rate of change of linear momentum of the system. You could call this, loosely speaking, force balance. And you say the forces have to be balanced. In statics, they balance each other. In dynamics, they balance the mass times the acceleration. Angular momentum balance equation is pretty much harder for most people at this point, which is you look at your system, you look at all of the external forces, you calculate the torques of all those forces, relative to some point C, and you can pick whatever point C you want, and you add up over all the particles in the system, the positions of all the particles relative to C, crossed with the mass of the particles and the absolute acceleration of the particles. And this is dynamics. And in statics, it's nice and simple. We put 0 here. So this is what you did in 202, and this is an approximation which is useful for all kinds of things. What happens in statics is you neglect the inertial terms. You neglect the terms having to do with mass times acceleration. If this is the only difference, why do we have a whole course on it? Is because it's tricky to work with this. Where's the tricky part? The tricky part is right in this box right here. Keeping track of the geometry of motion is a new complicated thing, which, by the end of the course, a third of you will have mastered it, a third of you will be pretty good at it, a third of you will still be struggling. It's just takes some effort to get it. You don't probably have what you need, even though the equations are all here. Okay, any questions about statics versus dynamics, or the previous part, or the previous part? How about in the back? Can you hear my voice clearly? Any problems in the back? Clear. How about in the back? Can you read the blackboard? Okay. If you ever have trouble hearing, ever have trouble reading the blackboard, tell me. The last thing you should know is that I have Alzheimer's. I was hired at Cornell under the Hire the Mentally Handicapped program. I've had Alzheimer's since I was in second grade or so. I make tons of mistakes at the blackboard. So if something looks wrong on the blackboard, okay, I was joking, right? Okay. I was half joking. Half joking. They didn't know they were hiring me under the Hire the Mental Handicap program. I make tons of mistakes at the blackboard, so if something looks wrong, don't be shy about correcting it. You're doing everybody a favor if you correct it. I'll have wrong subscripts, wrong letters, and so on. It will happen every class. Okay, any questions? Okay, now the next thing is what are the skills you need to get through this class? So the claim is all you're going to be doing is these things, mixing and maxing. Your goal is going to be to solve some kind of general mechanics problem. And what is a general mechanics problem? Is you are given some information about geometry, properties, and forces. Find other stuff. Find other information about geometry, properties, and forces. Okay, so this is your general goal, is to solve this general mechanics problem. For example, in statics, in the first part of TAM 2020, you were given a picture, geometry. You were usually told that the objects are rigid. Doesn't mean they are rigid. It means you idealize them as rigid. And you were told maybe the weight of the thing and maybe a coefficient of friction. By the way, under vocabulary here, we should probably add coefficient of friction, coefficient of restitution. And you were told to calculate some other forces or tensions or bending moments and so on. And this is the way it will go, except for now we'll add other things. The classic dynamics problem is you're given the properties and you're given some information about forces and you want to calculate where something is as time progresses. That's sort of the most standard dynamics problem. which is little distinguished from the most standard statics problem. So now what are the skills that you need to solve these problems? Well, you need vectors. And that means you have to know about dot product, you have to know about cross product, you have to know about plus, you have to know about unit vectors, you have to know how to manipulate things, maybe more than you had to in statics. And we will definitely push your vector skills here. We're not going to use them for a couple weeks at the beginning of this semester, but I would recommend you get geared up in your vector skills, which you could do by buying this book, for which I get no money, but you could buy it and read it. Or you could read it online. Okay, so you have vectors. What are some other key skills? We have now something we did not have so much of in statics. There's a little bit of it in statics. Remember in the bending moment equations, there were some differential equations. But now in dynamics, we're going to have a lot of differential equations. For example, if I give you an equation like this, I want you to just know what the solution of that differential equation is. Okay, without thinking any more, how many of you just know the solution to that equation, the general solution to that equation, just right here and right now? A, if you do. B, if you maybe kind of do. C, if you think you could figure it out. D and E, if it just looks mysterious to you. So there are a few simple differential equations like this that you just have to know. This is new material. Related to this, in the skills section, we have MATLAB, or computers. This could have been used in your statics class. When I teach statics, I do a lot of MATLAB. Other people don't. I think last semester you did not have a lot of MATLAB. Did you have any MATLAB in statics last semester? But you could use MATLAB a lot in statics. I am going to use it a lot in this class. You want to be able to do plotting with it. A fun thing that I think most of you will enjoy is you can do animation. You'll make little movies of things moving, and you can solve differential equations. And this is an empowering idea. There's a whole class in differential equations. Another poll: how many people are taking 293 now? How many took it before? How many are not taking it now and never took it before? Taking it now, took it before. Okay, so in 293, did you use MATLAB at all? Okay, so here's the thing. Yes or no? Yes? Old-fashioned technology. No? Okay, so there are all these pencil and paper methods for solving differential equations. Those can solve approximately 0 useful differential equations. On the other hand, the computer can solve all kinds of interesting equations. So you will get empowered with that in this class if you didn't get that in Math 293. Okay, so these are the skills. So this is the basic intro to the class. And the next thing I want to do is actually start the class. So any questions about anything on the blackboard? How about one question of any kind? $0.10 for a question of any kind. And just to show my honesty, I'm going to pay you 10 cents before I find out what the question is. Okay, what's the question?
You said the statics book was online, the dynamics book.
Both books are online.
Where?
Where? You will find them if you look. What? I can't. Oh, Google Ruina. R-U-I-N-A, Ruina. The basic answer to any question. Google Ruina. The book is online. I don't really advertise to you that it's online too much, except for I don't want to make you buy this book and I assign to you to read it. So you've got to find it online to read this book, which is assigned, some of it. I did a poll last time asking people how much they liked the book And I also asked them, did they buy it or read it online? And there's a high correlation between whether people bought it and whether they liked it. Okay, now, that could be a causal thing, like people who tend to read books bought it and therefore they liked it. But it could be that in this internet age, you are like me, and when you go to read things online, you just want quick information, and that you don't tend to put aside time to just read something slowly for half an hour. And I think you'll get more out of the book if you occasionally put aside time to read for sort of extended times. It's more than you asked, but did I cover your question? Yes. Okay. Okay. So I need to warn you that the big challenge in this class for you, for many of you, is going to be to do with vectors, and we're not starting right off with vectors. So I'm going to start off with a very freshman physics looking approach to things. I don't want you to get bad habits from this, so just be aware of the fact that you could build bad habits if you don't brace yourself for the two-dimensional and three-dimensional world that we're going to move into. Okay, so one-dimensional mechanics will be informal about our vector notation for now. So, the simplest thing to look at is a single particle. And what the word particle means is subtle. What we mean by it is we don't care about anything but its position. And we can get away with only worrying about its position. What do you mean by get away with? What do you mean don't care about? That gets to be more subtle, but for now you can think, I'm only going to pay attention to the position of a thing. So we're going to look at something which I'm going to call a particle. It's going to have some mass, and it's only going to move in one direction, which might be called the x direction, or the y direction, or the lambda direction, some direction that it's going to move, and it's going to have some force acting on it. And our basic governing equation are F is equal to ma. That A we can think about as being v dot. That V we can think about as being x dot. So we can write this as m v dot or as m x double dot. Anybody not know what the dots mean? Raise your hand if you don't know what the dots mean. Raise your hand if you do know what the dots mean. Okay. Now in what I've written so far, which parts of this board have I used? Well, I've used the laws of mechanics, F equals ma. I've used the geometry, this relationship between position and velocity and acceleration. What I have not used is the material properties. And where would those show up is in where this force comes from. So now there are all kinds of example problems that are of this type which we can solve. So for example, I will do a few sample problems. Let's do a particle falling in honey. So here's going to be the particle. It will have mass m. We'll pick a direction that we like. In this case, it's easiest to call down positive. And then we draw a free body diagram. So this thing I'm going to call is a free body diagram. What's a free body diagram? It's a picture of the system to which you are going to apply the laws of mechanics. That's the system for which you are going to use these equations. The law is you are not allowed to use these equations unless you draw a free body diagram. That's just the rule. You could say it's a law of mechanics. It kind of is. Or you could say Professor Ruina says, I have to do this. That's all there is to it. I don't like the idea of it. I think he's being pedantic, but just treat it as a bitter pill and just swallow it. You've got to draw a free body diagram. So what's this free body diagram? It's a picture of the system and all the forces on it. How do you figure it out? You go up to this particle and you say, well, it's being pulled on by the Earth. I would now like to fool it into thinking the Earth is there, even though I pulled the Earth away. So there's the particle sitting there. The Earth is gone, but it's got to be fooled. What force does it take to fool it? Is a force like that. What other force is there on this particle is being resisted by the flow of the honey. And what is the force of the flow of the honey? Is it c times the speed. So we're going to assume linear viscous honey. So that the force is proportional to the speed. When you draw letters next to arrows, the meaning of that is a letter multiplying a unit vector in the direction of the arrow. So here we have the gravity force is down. Here we take the quantity cx dot, which is a positive quantity if this particle is going down, multiply it by unit vector in that direction, and it gives an upwards force. This whole thing still makes sense if at the beginning of this problem, before I drew this on the blackboard, someone had launched this little BB up and it was not yet going down. This would still make sense. How does it make sense? This x dot would be negative because x is decreasing. And you multiply a negative number by a unit vector in that direction and you get a net downwards force. So this picture works even for the particle going up or down. You have to be careful with problems. For example, for quadratic drag problems, writing that equation is quite a bit more tricky, and I may get to that. Okay, so now I take, now that I've got my free body diagram, I go to linear momentum balance. How does linear momentum balance go? I take all of the forces acting on the system, and these are all of the external forces. For a particle, what are the internal forces? All the atomic bonds and things like that. They're forces, kind of, but we don't include them. They're not acting on the system from the outside. Equal to the mass total times the acceleration of the center of mass. In this case, that's just the mass times x double dot. What do we have for forces in the plus x direction? We have mg, and we have minus cx dot. So we can write this whole thing as mx double dot plus cx dot equals minus equals mg. So this is our differential equation, which we can write various ways. What are the various ways? We can put different things on the right or left-hand side of the equation. One thing we can do is we can write this in a simpler form because there's no x in this equation. So it looks like a second-order differential equation, but it's actually a first-order differential equation in disguise. It's actually this equation, mv dot plus cv equals mg. So it looks like a second-order equation, but it's actually just first-order. Little trick works out for some problems. Now, how do you write this equation? One way you can write this equation, which is kind of nice, is you write v dot equals mg minus cv all divided by m. So it's a third equivalent way to write the same differential equation. If we want to figure out how this particle moves, we have to solve that differential equation. How can we solve that differential equation? You can kind of remember it, you can integrate it, you can use separation of variables, you can use the computer, and you should be comfortable with all of these methods. But I just want to start out with a sort of qualitative way to look at this equation. And this is the way that we're going to look at differential equations all the time. Okay, questions before I do that? Anybody have trouble with the algebra and going from here to here to here. Okay, so what I recommend is that you sort of anthropomorphize or get into or visualize or make a cartoon of problems as best you can. The more you do that, the easier you'll find it is to actually do algebra. So here we have this football falling through honey. And what are we looking at is that if I let go of it, there's no viscous drag on it, but gravity's pulling down. It accelerates. So it goes faster and faster. But the faster it goes, the bigger the drag force. That slows it down. But how much does it slow down? Well, eventually that drag force balances the gravity force and everything's in balance. And it goes at constant speed. What happens if it happened to go a little bit faster, like there was a little perturbation? Is that stable going at that speed? Well, the gravity force stays the same, but the drag force gets bigger, so it will slow down. What happens if it's falling a little slower than that speed, called terminal velocity, steady state velocity, steady state solution? What happens if it goes slower than that? The gravity force is a little bigger than the viscous force, so it speeds up. So however you start this thing, it will always tend towards a steady state speed. How do you recognize that steady state speed in that equation? Well, steady state speed means the speed is constant. What does that mean the acceleration is? 0. So that means that we can find a steady state speed. How do we find the steady state speed? As we said, 0 is equal to mg minus cv. Or we say v steady state is equal to mg over c. That's right? That's called terminal velocity. Usually you hear this in reference to parachute jumpers whose parachutes don't open, or bombs that are falling, or satellites coming out of the sky, things that are dropping in the sky. It's usually not particles in honey. Okay, what does that mean the solution will look like? It means if we plot v as a function of time, if we start out with 0 velocity, it will tend up exponentially towards the steady state velocity. V steady state equals mg over c. If we start faster than that, it will tend towards from above. If we start by throwing it up, x dot is negative, which corresponds to throwing it up. It will eventually start going down and then tend towards this velocity. So this graph corresponds to x dot is initially negative, x dot is negative, it's going up, slowing down, eventually it's at 0 velocity. That's right here. And then it goes faster and faster and faster, but only so fast. On the other hand, if I throw it down too fast, it slows down and eventually gets to the right speed. Okay. Now how to do this algebraically, I'm going to skip right now. How to get exponential solutions, e to the minus something or other t. I have a different way that I want you to think about this, which is a different way of thinking about this. Is let's say we're doing the standard dynamics problems. The standard dynamics problems are you want to know how something moves. What do you do to figure out how it moves? Is you write down these equations, which inevitably turn into ordinary differential equations. To figure out how it moves, you have to solve these equations. Here's how the solution always works. You write these equations down. The equations have in them terms that have acceleration. You solve for the acceleration. How does that work? Here, we solve for the acceleration. If at one instant in time you know the acceleration, and you know the velocity, and you know the position, then you can tell what's going to happen at the next instant in time. How does that work? Well, if I know where I am and how fast I'm going, I multiply the speed times a little bit of time. That tells me how far I've moved. So by knowing my speed, I can predict my future position. Not very far in the future, just a little bit in the future, delta t. If I know my acceleration, I can tell my future speed. When your foot's on the gas pedal and you're accelerating, the speed of the car is increasing. The faster you're accelerating, the bigger the increase. So I can predict my future speed. But if I know my speed and my position at the new time, and I know the material properties of my system, that's enough for a well-posed dynamics problem to calculate the new acceleration. So looking at this equation, I say I can look a little bit forward in time. Therefore, I get my new speed. I already knew my last speed, because remember, I always had this equation in the background. Sorry. So if I knew my speed, I know my new position. Now I've gone forward a little bit in time. Now I've got a new speed. I can plug it in here. It gives me a new acceleration. I can go forward in time. I've got a new position and so on. Doing that integration over here with respect to position versus time, how do these various plots look? So let's label these plots A, B, and C. Okay, so plot A, let's just say we start out at 0 velocity and 0 position. So for all of these plots, let's say x at time 0 is equal to 0. What happens is it starts out with 0 velocity, so 0 slope, and then it builds up velocity and tends towards a steady state. So here's plot A, where this is a straight line, and the slope of this straight line is mg over c. What about B? Here we start out with a high velocity, bigger than this steady state velocity. So here's the steady state velocity curve. We start with a higher one, and then it tends to the steady state velocity and goes like this. There's curve B, which also has the slope mg over c. This also has the slope mg over c. And what about this case where I start out with a negative velocity? That means that the rate of change of x with respect to time is negative. It starts out with a negative slope. Eventually it gets to 0 velocity. I can label that point star. That point right here is star. And then it turns around and goes back up towards this steady state velocity. And this is curve capital C. Capital C, not to be distinguished with small c. And that also has the slope of 1 mg over c. Anybody want help thinking through any of those curves? Okay, the general idea is that you think of the laws of mechanics. In fact, this is an idea that is bigger than mechanics. It's for all thinking about understanding of the world. You think you understand the world. What that means is, if I tell you the present state of things, which in mechanics means positions and velocities, you know how they're going to change. But if you know how they're going to change, it means you're going to know the state in the future. And then you can use the rules to get the rate of change again. So what the laws of mechanics are, is they are a crystal ball for predicting the future. That's the way of thinking about what ordinary differential equations are. The laws of mechanics, dynamical systems, social dynamics, and so on. If you have an understanding of a situation, you know how to take the current state, use the workings to figure out how things will change, and that will predict the future. So if you see two people, two relatives at Thanksgiving, and one of them says, "Oh, Obama," and you say, "Uh-oh, they said Obama, but that one was voting for the other guy. What's his name?" What? Romney. You know the other one likes Romney. You know there's bad chemistry there. Just knowing that initial condition, they're both in the same room, one said Obama, you know they're about to get in a fight. So you predict there's a fight because you know the initial condition and you know the social dynamics. Okay? Same here. You know the initial conditions, the positions, velocities. You know the rules of mechanics. You predict the future. How do you do that in practice? Well, for a simple problem like this, you can draw graphs. You can almost get the solution in your head. You can remember how to solve first-order differential equations just by memorizing the exponential solution. You can use separation of variables, or you can resort to the computer to get solutions to the equations. Okay. Now I'm supposed to remember to erase ahead so I don't get in this situation. So I think what I'll do is I will erase ahead, and I'll give you a puzzle problem while the blackboard is drying. Make sure to get on the video how well I erase the blackboard. That's an important part of the. Because relative to other professors at Cornell, I might not be one of the greatest professors, but I think I am one of the greatest blackboard erasers. So that should be recorded. Okay, I have here two pieces of paper. They came from the same stack of paper, and I cut out little cones from this piece of paper. How did I cut them out? Is I went to Adobe Illustrator, a drawing program, and I drew these pictures in Adobe Illustrator, which I'll post on the web for you, and I followed the directions, which you can follow yourself. And I cut these two cones to ask myself the question, which one falls faster? Now, there's a famous experiment of Galileo at Pisa where he drops a big ball and a small ball, and he discovered that they both fall at the same speed. I had a basketball and a tennis ball, but someone stole my basketball. So this is a dice and a football. So they both fall at the same speed. Now you could take that as a law of nature, which is kind of the way Galileo thought about it. But then Newton came along and said, oh, it's all part of the laws of mechanics. So to get this result that the big one and small one fall at the same speed is actually a little calculation if you think of it from the laws of mechanics rather than a law in itself, which you should get comfortable doing. What about these pieces of paper where we cannot neglect air friction? Do they fall at the same speed or different speeds? The big one and the small one. Clearly air friction is important here, and this is reaching terminal velocity almost right away. If we think of it as this problem, we're going shh, and most of the time is spent basically on this curve. Anybody have an opinion about this? Yes? The big one will be slower. Any other opinions? Yes? They fall at the same rate, like the balls. Any other opinions? Yes? If you're not going to invest, you're not going to get anything back from the bank. I'm not going to tell you. So you can think about it. We'll discuss this next class.